Welcome everybody to our monthly webcast. Together with the Laser 2000 partner Photodyne, we will talk about the topic narrow bandwidth DBR laser diodes for quantum information systems and spectroscopy today. And this is the agenda. First of all, I will give a short introduction about your host, Laser 2000. Afterwards, I will be happy to introduce you to John Spencer from Photodyne, and he will give you an interesting insight into applications for narrow bandwidth laser diodes. In the end, of course, we will have a Q&A session with all the questions you have. Please therefore use the chat function that is a part of your control panel. You can send us the questions during the webcast, and we will answer the questions in the end. We will make sure to answer all of the questions, but maybe some elaborated questions may be answered via direct contact. But we will make sure that we answer all the questions. Okay. Let's start with the introduction of Laser 2000. Laser 2000 has more than 30 years of experience in all facets of photonics. We work with manufacturers from all over the world to provide our local customers with their products. For this purpose, we not only have contacts in Germany, but also in France, the Iberian Peninsula, and also Scandinavia. And also we have partners in the UK and Benelux. For us, it's very important to consult our customers in every stage of their project. In this way, we create the basis for comprehensive individual solutions that respond to every project, no matter how special the project is. A wide range of products allows us to provide our customers with every kind of photonic solutions. It starts with lasers and light source, but also everything else that is needed. Laser safety, test and measurement equipment, optics and optomechanics. Also a big part is machine vision and also fiber optics and networks. But today, the main category is laser and light sources, where the portfolio contains almost every type of laser. We have ultra short pulse lasers such as femtosecond lasers. We have a wide range of DPSS lasers, diode lasers, fiber lasers, gas lasers, and laser diodes of different types, which is the type Photodyne, today's presenter, is producing. And they have a special type of laser diode, very narrow bandwidth and also tunable. So now I'm proud to introduce you to the next speaker, John Spencer from Photodyne. Welcome, John, and thank you for being with us today.
Thank you very much, Simon. It's a pleasure to be here today for this webinar. I'll just note that it's June, and we would normally have expected to be getting ready to go to Munich this summer. But unfortunately, not this year, but we'll expect to be there in April when we have the Laser Munich trade show. We'll be looking forward to that very much. So again, thank you, Simon, and we're very, very pleased to introduce our company. I know many of you are already our customers, but those of you who are not, we want to tell you about our lasers and all the things that you can do with them. Photodyne is a manufacturer of lasers of exceptional stability. Our proprietary DBR lasers are designed and fabricated in our own wafer fab in Richardson, Texas, in the United States. These lasers are used for applications in quantum and other types of spectroscopy. In the area of quantum, the applications include clocks, magnetometers, gravimeters, and in spectroscopy for materials characterization, environmental monitoring, and biomedical diagnostics, including the types of spectroscopy of Raman, terahertz, and LiDAR, specifically differential absorption LiDAR for environmental monitoring. And what we'd like to say is that our proprietary lasers with their special capabilities enable proprietary customer capabilities. And that includes both in the research lab as well as in OEM applications. Our vision is to take the benchtop research laser, for example, a Ti-Sapphire laser, and take that functionality and put it on a semiconductor chip. The DBR laser is on a piece of gallium arsenide about 2 millimeters long and 1/4 of a millimeter wide. That tiny chip has all the capabilities at a specific wavelength that you would get in a Ti-Sapphire laser, including the power up to several hundred milliwatts, the line width of as low as 100 kilohertz, as well as very low noise and tunability over about a 2 nanometer tuning range. These very rugged and robust chips enable such products as handheld Raman spectroscopy, high-speed telecommunications network, such as for 5G networks with advanced atomic clocks. And then we see our customers using it in such applications for biomedical as electromagnetoencephalography or monitoring brain waves. And a characteristic of these lasers is that they're scalable semiconductors. So as volumes go up, the affordability goes way up. And on the bottom left of this chart, we see what we call our market pyramid. At the top of the pyramid, the lowest volumes are things like frequency standards, which right now would be used for research, for quantum applications, and so forth. As as our customers develop them into standard products, we see volumes going up, and that, of course, increases the affordability of them as we move into such things as biomedical applications, as well as metrology and various consumer applications. On the next slide, we describe in a little more detail the chip itself. We start with a gain medium. Photodyne is a vertically integrated producer. We design our own epi using proprietary software and modeling algorithms. And we have a very unique wafer fab process that allows us to produce the very precise features that you see on the graphic there on the right of this graph. That includes the ridge part of the laser where the current is injected and produces the high power up to several hundred milliwatts, depending on the wavelength and specific requirements. We use holographic lithography to pattern submicron gratings, sub-wavelength actually gratings that select the specific wavelength of the that the laser the mode of the laser. And then we can provide an epi to package solution. So depending on the customer's needs, we can provide all the way from a chip on submount to more advanced packaging applications. These lasers are designed for quantum and other types of very precise spectroscopy. They are single frequency, they are tunable, as I said, over about a 2 nanometer tuning range, and they are monolithic. They are used by researchers worldwide today, and they are scalable for OEMs tomorrow. Photodyne DBR lasers are a true platform technology. Specifically, I'm showing it here for quantum, that the platform of the DBR lasers supports quantum information systems applications as clocks, magnetometers, gravimeters, communications, and ultimately computers. When I say a platform technology, what I mean is that the DBR laser can be tuned and produced for very specific applications. For quantum, we see 3 pillars to this platform. And those are the 3 main wavelengths shown, whose term diagrams are shown here. Those wavelengths corresponding to the ytterbium ion, the rubidium atom, and the cesium atom. Those wavelengths being 369 nanometers in the near UV, a product that we currently have under development, with a very specific customer application in mind, specifically clocks and ultimately computers. And then right now, the mainline products, and where most of the work being done today is in the rubidium and cesium systems, 780 nanometers for the rubidium D2 line and 852 nanometers for the cesium D2 line. Now, as you can see from those term diagrams, there are multiple other wavelengths that support the quantum system, and that includes such wavelengths as 778, 776. We have other wavelengths such as 795 for the rubidium D1 and 895 for the cesium D1. We can provide a complete solution to our customers, and those supporting wavelengths span the range from about 740 nanometers to 1100 nanometers, with the 369 on our roadmap for the future. And as I said, we see that as a key wavelength and part of the pillars of our platform technology. Over the years, Photodyne has been continuously developing its products in response to the market. And I'll point out that the first Laser Munich trade show where we participated with Laser 2000 was in 2007, when we first introduced our rubidium lasers for 780. We had in 2007 we had 780 and 1083 being shipped to customers, and over the last 15 or so years, we have increased our range of offerings, more wavelengths, higher powers, and right now we have over 300 milliwatts at some wavelengths, 1064, 976, 852, and continue offering higher powers, better, narrower line widths, more stable, higher reliability, as well as additional designs such as gain chips and a wide range of packaging, including our various free space optics, free space packages with a VPS lens mounted on the submount, as well as butterfly packages with an isolator. Several years ago, we introduced our extended mode hop device, which has a 2 nanometer tuning range without a mode hop. And then more recently, we've introduced DBR lasers that operate up to 80 degrees C for those handheld applications that do not require a tech. And that's one where, by controlling the temperature, you reduce the power load of the system by not having that thermoelectric cooler. And we look for the future as working with our customers to identify new products. As I said, the 369 is on the roadmap, as well as other packaging solutions. And again, because we are a custom producer, we're able to meet our customers' specific needs. Quantum information systems is an area that has a lot of interest today, and it's one which is primarily in the research area right now, but there is a lot of interest in ultimately bringing complete products to bear here. Today, we see rubidium and cesium tuned DBR lasers being used for metrology applications such as atomic clocks, enabling faster internet speeds. In 3 to 5 years, we expect to see increasing applications in sensing, particularly the magnetometers and gravimeters for geophysical exploration and brain imaging. We'll see applications in position, navigation, and timing, and this being a very critical infrastructure application to have a GNSS independent, or have a PNT, position, navigation, timing system independent of GNSS. Greater than 5 years, we see further applications in metrology, even better atomic clocks, quantum cryptography, and over 10 years out there, quantum computing coming on mainline using either terbium ions or rubidium atoms. enabling such things as better artificial intelligence, drug discovery, and other things. So we're very excited about this, and that's a major part of our customer engagement and product development. For non-quantum applications, we have customer applications for such things as materials characterization, which includes Raman spectroscopy, terahertz Raman, where measuring the Raman signal very close to the exciting line, as well as and a key product there being our 300 milliwatt 785 nanometer extended mode hop DBR, which is enabling for these materials characterization applications. In biomedical, we're seeing applications in pumping optical coherence tomography, tunable lasers, again, terahertz spectroscopy, the key products there being difference frequency generation using a matched pair at 778 and 780 nanometers, for example, to produce terahertz. And then in environmental, we have applications ongoing for atmospheric monitoring, including LIDAR, differential absorption LIDAR, which allows very precise monitoring of water vapor concentration in the lower 5 kilometers of the atmosphere. And water vapor, with its high heat of vaporization, is the greatest contributor to weather in the lower atmosphere. And we have meteorological research organizations all over the world doing research on this technology, which is being used to measure not only the water vapor, but the turbidity of the atmosphere in the lower 5 kilometers, as well as the actual temperature. And quite interestingly, this uses some of our spectroscopy certified lasers for rubidium and other wavelengths in order to produce that capability. The key products there are 828 nanometers and 935 nanometer lasers for tuned for water vapor, 760 nanometers for oxygen sensing, which could be used, for example, for combustion monitoring. I'd like to discuss right now a case study in spectroscopy, which is frequency domain terahertz. This uses 2 precision paired DBRs with a gallium arsenide nonlinear chip to extract the beat frequency of those 2 DBRs. And in this case, we're calling them our spectroscopy certified terahertz application pairs, where they're specifically selected so that by tuning one of them high by temperature and one of them low by temperature, we start off by tuning them at equal wavelengths so that you have a 0 beat frequency, and then you raise one of them in temperature and lower the other one in temperature, and you can produce up to a 2 terahertz tuning range there. Required for that is an absolutely perfect LI curve for a matched pair that allows you to do that. And this is really a very novel and emerging application coming about, and there's a very interesting and informative paper produced or written by the National Physical Laboratory in the UK and Toptica concerning the industrial applications of terahertz sensing. We also see other commercial applications, and we call these beacons to the future, where they are ones that are under development right now, using the capabilities of DBR lasers to enable new applications and new products. Of course, telecom, with the rise of 5G networks requiring more accurate atomic clocks, is a major application coming on board. Biomedical diagnostics, terahertz spectroscopy has been found to be very sensitive to certain disease states by monitoring the composition of the human breath, using it as a diagnostic aid for the presence of disease. handheld Raman. We see more and more of that coming about as more precise Raman is required for novel applications, particularly materials characterization. And then we have the sensing for brain imaging, which replacing on the left, you see the thumbnail picture there of a cryogenic magnetometer, encephalograph, replaced by a laser version, which is doesn't require being put inside a huge instrument. Very sensitive for brain research as well as brain diagnostics. And then we have the weather forecasting. On the bottom thumbnail there on the left shows the instruments being rolled out for the initial testing of the weather forecasting, the dial application. And then there are other applications in defense, such as precision beam combining using the very precise and narrow line width lasers for that. Our support strategy and our customer strategy is shown on this slide. We're operating out of our home office as our sales team, consisting of Bob Davis, Vice President of Sales, and Esther Moreno, our inside sales manager. And many of you, our customers, may know those two. We have our product team led by Dr. Annie Zhang, our Director of Products. And of course, our contact in Germany, as I said, our long-term partners in Germany, Laser 2000. And I want to point out that Annie will be joining me for the question and answer session. And I want to point out that as our Director of Products, Annie certifies that each laser that we ship to our customers is certified, spectroscopy certified for this specific application. So if you order a 780 nanometer laser for rubidium applications, it is certified to operate on that transition at the specified temperature for its entire lifetime. So that is the basis of our spectroscopy certified product line. So thank you very much, Simon, and we'll go to the next step.
Thank you, John, very much for the great presentation. I hope it was as interesting for the audience as it was for me. I like to see that every wavelength fits to a certain atom, and also I think it's really great that you have the tunability without motifs. I think this is important, and this is the differentiation from other suppliers for such kind of laser diodes. So we now come to a Q&A session. We already received some questions, and of course you can still ask further questions. We don't want to leave the question unanswered. They will be included in our last minute questions in a few slides. Okay, hello Annie.
Hello Simon.
So Annie will support John for the questions. We already have the first questions. Which current controller do you recommend for the laser diodes?
Oh, okay, that is a question that we get very often. We do not put that information on the website, so we encourage you to contact us directly or through Simon through Laser 2000. So we absolutely have the partners with system integrators. So we know a lot of we know several lines of controllers, and the controller requirements really depends on the application. So there's servos and there's tabletop instrumentations. We have we would customize our response depending on the applications. So you do not find, although you do not find the information online, we are very happy to provide you with our recommendations. Just contact us.
Okay. The next question. I think, John, you mentioned it, but can you tell details about the current and temperature tuning rates and ranges for, in this case, especially for 852 nanometers, but I think it's almost the same for other wavelengths.
Absolutely, and Annie and her test team measure all of those on a daily basis. So that's she's ready to answer that question.
Okay, yes. So the temperature and current tuning characteristics of the DBR lasers is, as Simon said, is typical for this type of wavelength selective devices in the material system. I can give you the specific numbers, but I'd like to be precise, and the range depends on the wavelengths. It depends on the wavelengths and the powers. It's just as well. And also we have as John mentioned, the extended Mohawk configurations, which would extend the tuning range. So for the DBR lasers in general, the wavelengths can be tuned, of course, both by current and temperature. The main driver here is thermal, and as John mentioned, that it's typically in the 2 nanometer range, and we spectroscopy certify that, so that if the customer, for example, in this case, the A52 could be a cesium D2 line, and then we specify the cesium D2 line A52.3 vacuum A52.1 air in a certain wavelength range. So I hope that answered your question. If not, send us an email.
It's plus minus 2 nanometers, is it correct?
It can be plus minus 2 nanometers, but that depends on the temperature tuning, operating temperature range desirable. Typically, it's plus or minus 15 degrees C.
Okay.
And so that's corresponding to roughly plus and minus 1.5 nanometer.
Then the next question is about the optics. Can you recommend a package which is suitable for optics, especially in this case, it's collimation and polarization?
So the DBR lasers is by design it's polarized, and the polarizations, we typically have a polarization modes that's in one direction. There's a few customized epi design that have the polarization in the other direction, and the free space polarization is about 20 dB. Now for collimation, so our beam of the DBR is typical of an edge emitter, so it's an elliptical, but it's Gaussian-like and very easy to handle. So very simple optics for collimating the beams. However, a lot of our customers are very precise in terms of gathering all the power. Therefore, we would, for commercial off-the-shelf parts, we have a series of lenses that we can recommend for high NA to capture the beams in the fast axis. And we also, as John mentioned, have our in-house design of virtual point source lenses that not only captures the fast axis very quickly, and also reduce the astigmatism in both fast and slow axis. So yes, we have that information, and I can recommend the link for the white paper online as well.
What I see, many of our customers like the butterfly package with the fiber delivery, because then it's easier to bring the beam to your measurement setup.
Absolutely. So fiber pigtailing and beam delivery is on our product roadmap, and we do already have in-house partner solutions for butterfly packaging, both with and without isolator. And there are benchmark coupling efficiencies with and without isolator that some of the information is already online with the product bulletin. Some of the information you can acquire by contact Esther or myself.
Okay, then move to the next question. What are the typical line widths that you can achieve with the DBR lasers?
So DBR lasers is a prime candidate for narrow line width, single frequency device, and we specify a 1 megahertz line width, which is an upper limit for all our lasers across the wavelengths, across power levels, and across the packaging, except the butterfly without internal isolator, which will have optical feedback induced line width instability. But we have a solution for that, which is the isolated butterfly. We also have a white paper on the line widths on our website. Line width measurement is not quite standardized yet, but as John said, we have customers who provide feedbacks on the line width of free running our single diode, which is below 500 megahertz. And in-house, we use a dual heterodyne line width measurement where we routinely see line widths below 200 kilohertz.
Okay, I think we have one last question. Is the DBR technology capable to develop a stabilized laser in the power range of a few watt or for the visible light region?
So as John said, the visible light region is the current solution is not the direct DBR laser diode, and our pillar right now is the products is in the near IR and in the UV, which is the 369. So for the visible light region, it really is going to be dictated by the market. John, do you want to add on to that?
Yes, you know, this is not an area that we have a specific product for today. There are many existing lasers, fiber lasers, frequency double YAG lasers that can deliver that power in the visible. And we haven't seen the specific need yet that would justify the development of that. Not to say that it wouldn't be interesting, but at this point, it's not in the near-term roadmap.
Okay, this was already the last question. So thank you again, John and Annie. I hope it was interesting for the audience, and I hope you will join us for your next webcast, which is on the 7th of July, and it's about in situ monitoring of laser processing operation with high-speed sphere camera. Thank you and goodbye.
Thank you, Simon. Goodbye.
Thank you.